Welcome to lecture 10. We have 2 lectures remaining. This week we will start talking about series. Next week there's no lesson, and then in 2 weeks' time we'll finish talking about series. Last week we were talking about sequences, just a list of numbers, A1, A2, A3, A4, etc. If we take this list of numbers and we add them all together, then we have something called a series. To study a series, we need things called partial sums. Instead of adding all of the numbers in the sequence together, let's suppose we just want to add the first n terms together. This is called a partial sum of the series. And this is going to be our key tool to understand series, because the partial sums are just a sequence, and we know a lot about sequences now. We say that a series converges if and only if the sequence of partial sums converges. If Sn converges to a number S, say, as n tends to infinity, then we say that the number S is the sum of the series, and then we can write that the infinite series of AK is equal to S. If a series does not converge, then we say that the series diverges. Let's just talk about notation briefly. If I write capital sigma from k is equal to 1 to infinity AK, that might mean 2 different things. It might mean the series A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 plus, and then goes on forever. And that might converge or it might diverge. But sometimes when I write that notation, I mean the actual sum of the series. In other words, the limit of the partial sums. I need you to be aware and understanding what I mean every time I write that notation from the context. Our first series, 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus, and then that goes on and on forever. The partial sum, the sum of the first n terms, so 1 plus 1 plus 1 plus 1, n times. Partial sum Sn, of course, is just equal to n, because it's n ones added together. And we know that that sequence converges to infinity. There should be another 1 just here. So this series diverges. Another example. Have a look at this rectangle, a width 2 and height 1. So the area of this rectangle is equal to 2. If I chop this rectangle into half, the area of the blue square must be 1. Chop the white part in half again. The area of this piece must be a half. The area of this piece must be a quarter, and keep going. We'll keep chopping the white section into half. And look at the bottom. 2, the area of the rectangle we started with, is 1 plus a half plus a quarter plus 1 over 8 plus 1 over 16 plus 1 over 32 plus 1 over 64 plus 1 over 128 plus 1 over 256, etc. This is a convergent series. We can add up an infinite number of positive numbers, but we are converging to a finite number. Let's make that a little bit more general. Now let's look at 1 plus x squared plus x cubed plus x to the power 4, etc. This is the same as I did on the previous slide. On the previous slide, I had x equal to 2. Let's just make this more general. Now let's let x be any real number. The partial sums are the sums 1 plus x squared plus x cubed plus dot 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 plus x to the power n minus 1, because x to the power n minus 1 is the nth term. And I want to look at 1 minus x multiplied by the partial sum. So that's Sn, and then minus x multiplied by Sn. Now, the way I've written this, you can see a lot of these terms are going to cancel. I have plus x and then minus x. I have plus x squared and I have minus x squared. Almost all of these terms are going to cancel, and we're just going to be left with 1 minus x to the power n. If x is not equal to 1, we can divide both sides by 1 minus x, and we can get the formula Sn is 1 minus x to the power n over 1 minus x. Okay, now let's study this geometric series for different values of x. First of all, if x is equal to 1, then the partial sum is just 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. And that diverges. So the series diverges if x is equal to 1. If the absolute value of x is less than 1, then the partial sums, 1 minus x to the power n over 1 minus x, converges to 1 over 1 minus x. So we can say that if the absolute value of x is less than 1, then the geometric series converges and its value is equal to 1 over 1 minus x. What about if x is equal to minus 1? Then Sn is 1 minus 1 to the power n over 2. And think about that. We have a sequence which goes 1, 0, 1, 0, 1, 0. That sequence doesn't have a limit. So the geometric series doesn't have a limit. Geometric series diverges. If the absolute value of x is greater than 1, we can look at the absolute value of the partial sums. And we can see that that diverges to infinity. If x is strictly greater than 1, then we have partial sums which just keep getting bigger and bigger and bigger. If x is less than minus 1, then we're going to have Sn which is positive, negative, positive, negative, positive, negative, and in magnitude, in absolute value, is getting bigger and bigger and bigger. So we can say that if the absolute value of x is greater than 1, then the geometric series diverges. Let's write that as a theorem. A geometric series converges if the absolute value of x is less than 1, and it diverges otherwise. Moreover, if the absolute value of x is less than 1, then we have a formula for the sum or the value of the geometric series. There's a typo on the next slide. If you're the first person to spot the mistake, then write it in the chat. This is a geometric series. I've written the formula at the top. 7 plus 7 over 3 plus 7 over 27 plus 7 over 81 plus 7 over 243 plus dot, dot, dot. Geometric series needs to start at 1. So we take a factor of 7 outside and we just look at what we have left. 1 plus a third plus 1 over 27 plus 1 over 81. That's 1 plus x squared plus x cubed plus x to the power 4, etc., where x is 1/3. So use the formula at the top. In the bracket, we have 1 over 1 minus x, 1 over 1 minus 1/3. And when we calculate that, we get 21 over 2, or 10.5. Did anybody spot the mistake on this slide yet? Okay, well, let me tell you the mistake. The mistake is I've missed a term out here. There should be a 7 over 9 here. Because 1/3 squared is not 1 over 27. 1/3 squared is 1 over 9. So there should be an extra term here. Likewise, just here, there should be a 1 over 9. An example from the textbook: express the repeating decimal 5.232323 as the ratio of two integers. This is another geometric series question. We're going to write this as 5, and then for the first two decimal digits, the 3, we're going to write this as 23 over 100. And then for the next two, that's 23 over 10,000. And then the next two is 23 over a million, etc. Forget about the 5 over at the moment. We'll deal with that later. What we have is 23 over 100 multiplied by a geometric series. Remember, a geometric series always starts at 1. So take the other numbers out. We have 1 plus 1 over 100 plus 1 over 100 squared plus dot, dot, dot. This is a geometric series where x is equal to 1 over 100. So we use our formula, 1 over 1 minus x, or 1 over 1 minus 1 over 100. And when we calculate that, of course, we get 100 over 99. The hundreds cancel, and we're left with 23 over 99. Now we'll just take care of the plus 5, and we'll get our answer. I'll leave this for you to read in your textbook later. Enough about geometric series. Let's move on to other series. What about this one? Does this one converge or diverge? The series of 1 over n multiplied by n plus 1. To understand it, we want to look at the partial sums, but before we do that, I want to write this in partial fractions. A1, that's 1 over 1 multiplied by 2. I want to write as 1 minus a half. A2, I want to write as a half minus a third. A3, I want to write as a third minus a quarter. In general, I want to write an as 1 over n minus 1 over n plus 1. And I'm doing that to make the partial sums easier to understand. Sn always means the sum of the first n terms in the sequence, in the series. So that's a1 plus a2 plus a3 up to an. So that's 1 minus a half plus a half minus a third plus a third minus a quarter minus a fifth, etc. Now you can see why I'm doing this. Why did I write the terms like this? Because I have minus a half plus a half, and they will cancel. Minus 1/3 plus 1/3, and so on. Almost all of these terms are going to cancel, and we're going to be left with 1 minus 1 over n plus 1. Does this sequence of partial sums converge or diverge? Of course it converges to the number 1. Because Sn converges, therefore the series converges, and it has the value equal to 1. Theorem, the sum rule. If we have two convergent series, and it only works if they're convergent, then we can add them together, and their values also add together. The series of AK plus BK is going to be S plus T, and this will also be convergent. Let's do the proof very quickly. Let's suppose that Sn is the partial sum of the first series, and let's suppose that Tn is the partial sum of the second series. Because these two series converge, we know that these two sequences of partial sums also converge. So let's suppose, well, we know what they converge to. We know that Sn converges to the number S, and we know that Tn converges to the number T. Now, let's look at the partial sum of AK plus BK, just the first n terms. That's A1 plus B1 plus A2 plus B2 plus A3 plus B3 plus ... We can rearrange this. Just look at the A's. A1 plus A2 plus A3 plus A4 plus ... plus AN, that's just Sn. And if we just look at the B terms, B1 plus B2 plus B3 plus B4 plus ... plus Bn, that's just Tn. And Sn plus Tn, we know that we can add two convergent sequences together, and we just get S plus T. And that's the end of the proof. Therefore, the series AK plus BK converges, and its value is equal to the sum of the series of AK and the series of BK. So to summarize, if two series are convergent, then we can add them together. We also have a constant multiple rule for series. Again, if we need to have a convergent series, and if we do, then we can multiply the series by a number. I'll leave this for you to prove. The divergence test, the first of our tests for convergence, is actually a test for divergence. If AN does not converge to 0, if AN is not a null sequence, then the series of AN always diverges. Let's prove this. As always, to understand a series, we look at the partial sum. So let Sn be A1 plus A2 plus A3 plus ... plus AN. which we're pretty much always going to be doing. I'm going to use a type of proof called proof by contrapositive. I'm actually going to prove that if the series converges, then AN must converge to 0. That's logically equivalent to the statement in the divergence test. So if we're supposing that we have a series which converges, that means Sn converges to S. But then the slightly different sequence, Sn minus 1, must also converge to S. And therefore An, which is Sn minus 1, converges to S minus S, or 0. So this proves that if a series converges, then An must be a null sequence. By the type of proof called proof by contrapositive, this is logically equivalent to saying if An is not a null sequence, if An does not converge to 0, then the series of An diverges. Sometimes we might need it the other way around, so let me just write that as a corollary. If a series converges, then An is a null sequence. Now, just give me a warning here. It's true that if a series converges, then An converges to 0. But it's not true the other way around. It's not true that if An is a null sequence, then the series An always converges. Be careful here. For example, let An be equal to 1 over n. Then clearly An converges to 0 as n tends to infinity. But does the series of 1 over n converge or diverge? The partial sums, 1 plus a half plus a third plus dot 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 plus 1 over n, clearly that's an increasing sequence. Now what we can do is we can look at S2 to the power n. Instead of looking at Sn, I want to look at S2 to the power n. And I'm doing that because I want to group the terms up like this. 1 and a half can just stay by themselves. Then I'm going to group 2 terms together. And then I'm going to group 4 terms together. And then I'm going to group 8 terms together. And then I'm going to group 16 terms together, and so on. Why am I grouping them like this? Because a third is bigger than a quarter. A fifth is bigger than an eighth. A sixth is bigger than an eighth. 1/7 is bigger than an eighth. But look what we have here. A quarter plus a quarter is a half. 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8 is a half. 1 over 2 to the power n plus 1 over 2 to the power n plus 1 over 2 to the power n. And we have n of these. So we have 2 to the power n minus 1 of these. So this is equal to a half. I get 1 plus a half 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 plus a half. And this is going to diverge. S2 2 to the power n is not bounded above, so Sn is not bounded above. What did we learn last week about sequences which are increasing and which are not bounded above? We learned last week that sequences which are increasing and not bounded above must diverge to infinity. So the series of 1 over n diverges. So here we have a series where the terms an is a null sequence, but the series diverges. So hence the warning I gave on the previous slide. This is a very important series. We're going to need this later today, or we're going to need this next week. So let's write this as a lemma. Please remember that the series of 1 over n diverges. Let's do another one. What about the series 3n plus 1 divided by 5n plus 1 all to the power of 4? Does this converge or diverge? Bn converges to 3 over 5 to the power of 4, and that's not 0. So straight away we know that this series diverges by the divergence test. If Bn does not converge to 0, then the series diverges. And that's all we need to say. Does the series of 1 over the square root of n converge or diverge? Well, the first thing to note is that we can compare this to 1 over n, because 1 over the square root of n is bigger than 1 over n. And we know that the series of 1 over n diverges. In terms of partial sums, if we use the letters Sn and Tn, we know that Sn must be bigger than Tn. And we know that Tn converges to infinity because the series of 1 over n diverges. So Sn is bigger than something which tends to infinity. So Sn must tend to infinity as well. So therefore, the series of 1 over the square root of n must diverge. What we've done is we've learned about this series by comparing it to another one that we already understand. We'll talk about that again later. First, I want to introduce a test called the integral test. I think my numbers have gone slightly wrong here. This should be section 9.3, shouldn't it? Never mind. Let's suppose we have a function. The domain of the function will be between 1 and infinity, and its range, or sorry, its target will be between 0 and infinity. And I want this to satisfy 3 rules. I want it to be continuous, I want it to be decreasing, and I want it to always be positive. So let's just draw some function like this. Any function which satisfies these 3 rules. And I'm interested in the area underneath this function. Between 1 and n, say, we'll call this capital I-n. In the picture, I've drawn capital I6, the area between 1 and 6. I'm also interested in putting some rectangles underneath the function. F1, F2, F3, F4, etc. These are rectangles of height, Fj for each j, and width 1. So the area of each one of these rectangles is going to be Fj. If we add up the first n rectangles, I'm going to call that Sn. Now, for the time being, let's forget about F1 and just look at the green rectangles. Note that the green rectangles fit inside the purple area. So F2 plus F3 plus F4 up to Fn is always going to be smaller than In. What's the difference between them? This orange section is going to be the difference between I6 and F2 plus F3 plus F4 plus up to Fn. And another way of writing this green section would be Sn minus F1. So the difference between these two regions is going to be In minus Sn plus F1. That's the orange shaded section. Okay, now as n increases, In minus Sn plus F1, the orange piece, is going to increase. Every time we add on an extra piece, the area of the orange bits gets bigger. So this is an increasing sequence. F1 is just a constant. We don't need to worry about that. We can say that In minus Sn is an increasing sequence. The next thing I want to say is all of these orange pieces will fit inside the blue rectangle. Look, just slide them across to the left like this. All of these orange pieces are going to fit inside the blue rectangle. We can see from this picture that the orange pieces are going to be smaller in total than F1. Cancel the F1s. We can say that In minus Sn is always going to be less than or equal to 0. So what have we learned here? We've learned that In minus Sn is an increasing sequence which is bounded above. What does that tell us? increasing sequence which is bounded above always means convergent sequence. This is a key idea. Let's write this as a lemma. If f is a positive decreasing continuous function, if Sn is the sum from f1 to fn, and if In is the integral between 1 and n of fx dx, then In minus Sn is a convergent sequence. We can use this key fact to prove the integral test. Again, if f is a positive decreasing continuous function, and if the integral from 1 to infinity of f of x dfx is finite, then the series of fn converges. If the integral is equal to infinity, then the series of fn diverges. We've done most of the work already to prove this. We're going to use the previous lemma. Let Sn and In be as we've used them before, and let Cn be the difference between these two. We know that Cn is a convergent sequence, so let's suppose Cn converges to some number C. Because fx is always positive, Sn and In are both increasing sequences. So there's two possibilities. Either In is bounded above or In is not bounded above. Let's look at case 1 first. If In is increasing and bounded above, then In must converge. But if In converges and C converges, Cn converges, then Sn must converge as well. So if In is bounded above, in other words, if the integral is finite, then the series must converge. Case 2, if In is not bounded above, that's the same as saying that if the integral is equal to infinity, then Sn must also converge to infinity, so the series must diverge. And that's the proof of the integral test. Now we can start using it for some examples. For which values of alpha greater than 0 does the series 1 over n to the power alpha converge? I want to use the integral test. So I want to get a function, and then I want to integrate that function, and I want to see, is the integral equal to infinity or is it equal to a finite number? So my function is going to be 1 over x to the power alpha. This function is continuous, it's decreasing, and it's positive. So I can calculate the integral of this function. I'm going to calculate the integral between 1 and n, and then I'm going to take the limit as n tends to infinity. Now, if alpha is equal to 1 first, we know that the integral of 1 divided by x is just the natural logarithm of x. If alpha is not equal to 1, again, we know how to do this integral. We know antiderivative is 1 over alpha minus 1 multiplied by minus 1 over x to the power alpha minus 1. Let's look at some different cases. First, what happens if alpha is strictly greater than 1? Then the limit of In is 1 over alpha minus 1, which is a finite number. So if alpha is greater than 1, the series must converge by the integral test. Next, let's look at alpha equal to 1. If alpha is equal to 1, then In converges to infinity as n tends to infinity. So the series must diverge by the integral test. And finally, if alpha is between 0 and 1, then again, we can find that In converges to infinity. So the series diverges by the integral test. Let's just recap that. Again, this is an important series, so let's write this as a field. The series of 1 over n to the power alpha diverges if alpha is between 0 and 1, and converges for alpha strictly greater than 1. Another example. Consider the series from n equal 2 to infinity of 1 over n natural logarithm n. Question for you to think about: why am I starting at n equal to 2 here instead of n equal to 1? Use the integral test just to decide if this series converges or diverges. We need a function. If we're going to use the integral test, we always need a function. Define f of x to be 1 over x natural logarithm of x for x greater than or equal to 2. This function is continuous, decreasing, and positive. So we can calculate the integral. I want the integral between 2 and infinity of this function. Anytime we do an integral with an infinity, and what it really means is the limit of an integral with a letter here. So I'm doing the limit as n tends to infinity, integral from 2 to n f of x dx. And when I calculate this, and I leave the details for you to check, I get infinity. So, because the integral is equal to infinity, what do we know about the series? Does the series converge or diverge? The integral test says if the integral is equal to infinity, then the series diverges. If the integral is less than infinity, then the series converges. So therefore, this series must diverge. Let's do a couple of examples from the textbook. the series of n e to the power minus n squared. Does this converge or diverge using the integral test? Well, we look at what we have here. We have n e to the power minus n squared, and then we want to use the same function. So we want to use x e to the power minus x squared, which is the same as x over e to the power x squared. And we calculate this integral between 1 and infinity. And this time we get 1 over 2e, which is a finite number. Because this is a finite number, because it's less than infinity, the series converges. Another example from the textbook, going through very quickly. 1 over 2 to the power ln n. Our function is going to be 1 over 2 to the power ln x. We're going to integrate that between 1 and infinity, and we see what we get. And here we get equal to infinity. Because the integral is equal to infinity, that means the series diverges. The next section, which I think should be section 9.4, is about the comparison tests. I want to introduce 2 more tests for convergence. The first one is just called the comparison test. Let's suppose we have 2 series of non-negative real numbers. In other words, we want an to be always greater than or equal to 0, and we want bn to be always greater than or equal to 0. And I want to suppose that 0 is less than or equal to an is less than or equal to some constant k bn for all n, where k is a positive constant. And I want to suppose that the series of bn converges. The theorem says that then the series of an also converges. Now you can think of this as similar to the sandwich rule. If the bigger one converges, then the smaller one should also converge, because the smaller one is squashed between 0 and the bigger one. Very quickly, let's go through the proof. Again, we need to talk about partial sums to prove this. So let Sn be the partial sum of the first one and Tn be the partial sum of the second one. Because AK and BK are always positive, that means that Sn and Tn are going to be increasing sequences. Because we know that the series of Bn converges, that means Tn converges to some number T. So that means Sn, which is A1 plus A2 plus A3 plus dot 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 plus n, is smaller than KB1 plus KB2 plus KB3 plus dot 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 KBn, which is KTn, which is smaller than KT. So this proves that Sn is an increasing sequence which is bounded above. What do we know about increasing sequences which are bounded above? The same question I asked earlier. It's the same fact we're going to be using again and again and again. An increasing sequence which is bounded above is always convergent. So that's the end of the proof. corollary of this, same idea. If we have an is bigger than some constant kcn, and if the smaller one diverges, then the bigger one must also diverge. And the way we can prove this is just by letting capital K be 1 over K. Then the Cn is less than or equal to capital K An, and by the comparison test, we would know that if the series of An converges, then the series of Cn converges. But by proof by contrapositive, this is logically equivalent to saying if the series of Cn diverges, then the series of An diverges. And that's all we would need to do for the proof. Let's go back to the comparison test and let's make one change. When we did the comparison test, I said it had to be true for all natural numbers n, but let's make it a little bit more general. Remember, when we're talking about sequences and series, we don't care what happens at the start. We only care what happens at the end of the sequence or the series. So we could have any sort of crazy behavior happening at the start, as long as the crazy behavior is only at the start, only just here. If after that we have our inequality of green being smaller than blue, then we would have the same thing happening. So as long as we know that after some number n0, we have the same behavior, we can use the same facts as before. For example, does this series converge or diverge? Now, note 2 over 4n minus 1. I want to make this smaller. One way to make this smaller is by making the bottom bigger. 4n is bigger than 4n minus 1, so 2 over 4n is smaller than 2 over 4n minus 1. But that's just 1 over 2n, or half multiplied by 1 over n. That's a constant multiplied by 1 over n. We know that the series of 1 over n diverges. And now we have a series which is bigger, up to a constant, than something which diverges. If we're bigger than something which diverges, then it must diverge. So our series must also diverge. The second key test in this section is called the limit comparison test. This time we need two series of strictly positive real numbers. And we can't allow them to be 0 this time. This time they both must be strictly positive. And we need three things to be true. We need that an divided by bn must converge to some number L. L must be a real number, and L must not be 0. Then the theorem tells us that one of two things must be true. Either both of these series converge, or they both diverge. Let's go through the proof quickly. If L is not 0, and if an over bn converges to L, then straight away we can say L must be a positive number. So there exists some that number capital N, such that if N is greater than capital N, the idea is from last week. AN over BN must be close to L. How close? We can say closer than L over 2 if we wanted to. We can insist that AN is between L over 2 BN and 3 over 2 BN. But that sort of looks like what we were using in the first test, in the comparison test. Using the facts from before, if the series Bn converges, then we can use the previous corollary to say, therefore, the series An also converges. Using this fact. Or if the other way around, if we know that the series An already converges, use this inequality to say, but therefore, the series Bn must also converge. So if Bn converges, then the series of An converges. If the series of An converges, then the series of Bn converges. So these two series must both converge or they must both diverge. And that's a good place for a break. Let's take a break until 2:15. And now let's continue. In the next lemma, I'm claiming that the series 1 over n squared converges. We actually already know this because we've used the integral test to do this, but let's do this a different way. We can do this by comparing it to the series 1 over n plus 1. We already know that the series 1 over n plus 1 converges. I want to use the limit comparison test. So I want to look at an divided by bn. Note that an over bn converges to 1. I have here a number which is a real number and which is not 0. So it's okay to use the limit comparison test. The limit comparison test tells us that both of these series must have the same behavior. Either they both converge or they both diverge. But we already know that one of these converges, so that means that the other one must also converge. By the limit comparison test, the series of 1 over n squared also converges. In fact, 1 over n to the power alpha converges for all alpha greater than or equal to 2. This time we could prove this using the comparison test. Because if alpha is greater than or equal to 2, 1 over n to the power alpha is smaller than 1 over n squared. We know the series of 1 over n squared converges. If the bigger one converges, then the smaller one must also converge. Again, we already know this because we've already done this with the integral test, but this is another way to prove this. We could also show that 1 over n to the power alpha diverges for all alpha less than or equal to 1. We know it's true for alpha equal to 1, and we also know that 1 over n is smaller than 1 over n to the power alpha if alpha is less than or equal to 1. If the smaller one diverges, then the bigger one must also diverge. Sine 1 over n, the series of sine 1 over n. This diverges. Why? Because I want to compare it with 1 over n. Again, I'm going to do limit comparison test. I'm going to do an divided by bn. So that's sine 1 over n divided by 1 over n. And that converges to 1. Because the value here doesn't matter, the number 1 doesn't matter. All that matters is we have a real number which is not 0. The limit comparison test says either they both converge or they both diverge. We already know that one of them diverges, therefore the other one diverges as well. There's more examples in the textbook. I'll let you read through your textbook and read some more examples using the comparison test and the limit comparison test. I want to move on to what should be section 9.5, absolute convergence, the ratio and root tests. First, the ratio test. I want to have a series of strictly positive real numbers. We're not allowed to have 0 this time. They must always be strictly positive. And this time I'm looking at an plus 1 divided by an. I'm not comparing two different series. I'm only looking at consecutive terms in this series. Suppose that this converges to some number L, which is either a real number or is infinity. Now, depending on the value of L, we have some different answers. If L is strictly less than 1, then we know that the series converges. If L is strictly greater than 1, then it diverges. If L is equal to infinity, then again it diverges. Let's prove this. First, case 1. Suppose that L is strictly less than 1, and then I want to choose a value of k between L and 1. Then, of course, k minus L is positive. You can think of k minus L as our epsilon here. Because an plus 1 over an converges to L, and that means that there exists a natural number capital N such that if small n is bigger than capital N, an plus 1 over an is close to L. How close? As close as we want. In fact, we can have it closer than k minus L. That's the epsilon we're choosing to use here. But that's the same as saying that an plus 1 is smaller than kan. But then if n is bigger than capital N plus 1, an, which is a positive number, is smaller than k multiplied by n minus 1, which is smaller than k squared multiplied by an plus 2, and so on. All of the way up to kn multiplied by a capital N plus 1 over kn capital N plus 1. Now, this term in the brackets is a constant. So really we have that an is trapped between 0 and k to the power n multiplied by some constant. The series of kn is a geometric series. We don't understand those already. That's the first type one we looked at today. That converges because k is between 0 and 1. So by the comparison test, our series also converges. Case 2, what do we do if capital N is greater than 1? I'm going to be using the divergence test. Do what we did before, but I've skipped some steps here. We can show that there exists capital M such that if n is greater than capital N, then an plus 1 over an is greater than 1. In other words, an plus 1 is bigger than an. But then we have that an is bigger than an minus 1, which is bigger than an minus 2, and which is bigger than is bigger than is bigger than is bigger than an plus 1. That proves that an is not a null sequence. An does not converge to 0. So straight away we can use the divergence test to see that the series of an must diverge. For the final case, L equal to infinity, I'm going to leave that for you to prove. let me just note that if L is equal to 1, then the ratio test tells us nothing. If we end up with equal to 1, then we have to use a different test. For example, let's look at 1 over n and 1 over n squared again. We know that the series of 1 over n diverges and the series of 1 over n squared converges. If we tried to use the ratio test on these two, if we looked at an plus 1 over an, took the limit, we would get 1. If we tried to use it for bn, bn plus 1 over bn, take the limit, we get 1. Two series here. They both have a limit of the ratio equal to 1, but one of them converges and one of them diverges. If we ever get L equal to 1 when we're trying to use the ratio test, then we know we can't use that test. We have to use a different test instead. One more thing I want to note is that, again, looking at 1 over n, note that we always have an plus 1 over an is less than 1. But that's not relevant here. Remember, when we use the ratio test, we're not looking at an plus 1 over an. We're looking at the limit of an plus 1 over n. Here's a nice series that we could use the ratio test for. Does the series of 2n factorial divided by 7n, n factorial squared, converge or diverge? Let's call this Zn. We need to choose a letter for it. Doesn't matter which letter we choose. Then note that Zn is always strictly positive. I want to look at Zn plus 1 divided by Zn. In green, I've got 1 divided by Zn, and in orange, I've got Zn plus 1. A lot of these terms are going to cancel. There's 7n plus 1 on the bottom and 7n on the top. Most of these are going to cancel, and we'll just end up with a 7 on the bottom. Next, there's a 2n plus 2 factorial and a 2n factorial. Most of these terms are going to cancel, and we're just going to be left with 2n plus 2, 2n plus 1. Likewise, there's a n plus 1 factorial squared and an n factorial squared. Almost all of these terms are going to cancel, and we'll just end up with n plus 1 squared on the bottom. Divide through by n squared, and then take the limit. We get 4 over 7, which is less than 1. So what do we know? So far, 2 people have voted converges, 1 person has voted diverges, and 9 people I'm still waiting for you to choose. The ratio test says that if the limit of Zn plus 1 over Zn is less than 1, then the series converges. Another one, does the series of n squared e to the power minus n plus 1 converge or diverge? We need to choose a letter, it doesn't matter, I'm choosing the letter y this term. Yn is always strictly positive, and therefore we can look at yn plus 1 divided by yn. When we simplify yn plus 1 over yn and then take the limit, we get 0, and 0 is less than 1. Because we're less than 1, it must converge. Now, let's suppose we have a series where some of the terms are positive and some of them are negative. We might have a series which might converge or might not converge. For example, if we had the geometric series 5 minus 5 over 4 plus 5 over 16 minus 5 over 64 plus 5 over 256, etc. This is a geometric series where x is minus a quarter. And the absolute value is minus a quarter is less than 1. So this geometric series converges. However, if we had the geometric series 1 minus 5 over 4 plus 25 over 16 minus 125 over 64, etc., etc., that's a geometric series where x is minus 5 over 4. And because the absolute value of minus 5 over 4 is bigger than 1, this geometric series diverges. For the rest of this section, we're going to be looking at a series where we have a mixture of positive and negative terms. If we have a series of real numbers, and if we could take the absolute value of each an, and if then we had a series which was convergent, then we say that the original series is absolutely convergent. Or to say another way, we could say it converges absolutely. A theorem. Every absolutely convergent series is convergent. Now, what that says is, if the series absolute value of an converges, then the series an converges. Let's prove this. Let the series of an be absolutely convergent. In other words, we're going to start by supposing that the series absolute value of an converges. Now, some of these an might be positive and some of them might be negative. I want to separate them out. For the positive terms, I'm going to call them bn. Anytime an is positive, I'm going to let bn be equal to an. And if an is negative, we'll just let bn be 0. For cn, we're going to do the opposite. Anytime an is positive, we'll just take Cn is 0, but if an is negative, we're going to let Cn be minus an. And I'm doing that so that an is equal to bn minus cn, and so that bn is always positive and cn is always positive. So just as an example, if our original series is 1, 2, minus 1, 4, minus 5, say, then the series bn is going to be 1, 2, 0, 4, 0. And the series cn is going to be 0, 0, 1, 0, 5. It's just separating the positive terms from the negative terms, and then all of the negative terms we're going to make positive. Right. Now we've done that, I need to introduce some partial sums. Sn is going to be the absolute value of a1 plus the absolute value of a2, etc. Tn is going to be a1 plus a2 plus a3, etc. Rn is going to be b1, b2, b3, and un is going to be c1, c2, c3, etc. 4 different partial sums. We know that Sn converges because we know that An is absolutely convergent. We want to prove that Tn converges. Now, because the absolute value of Ak is always greater than or equal to 0, we know that Sn is increasing. So Sn must be always less than or equal to S for all n. Hence Rn, which is b1, b2 plus b3. Remember, b1 is either equal to an or it's equal to 0. b2 might be equal to a2 or it might be equal to 0. b3 might be equal to a3 or it might be equal to 0. So certainly we have smaller here. Certainly Rn is smaller than Sn and Sn is smaller than S. Because Bn is always greater than or equal to 0, Rk is an increasing sequence which is bounded above. Is this fact again? Increasing sequence which is bounded above. What does that mean? That means convergent. So Rn must converge to R. Similarly, and I'm not going to do the whole argument, Un must also converge to some number. Let's call it U. But then we're finished because Tn is just Rn minus Un. Rn converges to R, Un converges to U, so Tn must converge to R minus U. And that's the end of the proof. Therefore, the series of An converges. So now we know that if the series of An is absolutely convergent, then the series of An is convergent. But the converse is not true. Having a series of An be convergent does not imply that the series of An is absolutely convergent. An example would be letting An be minus 1 to the power n plus 1 over n. I'm going to show you later that 1 minus a half plus a third minus a quarter plus a fifth, etc. is convergent, but we already know that 1 plus a half plus a third plus a quarter plus a fifth, etc. is divergent. So just be careful here. One way this implication is true, the other way the implication is false. A corollary of this is the triangle inequality for series. If we have an absolutely convergent series, then the absolute value of the series of an is less than or equal to the series of the absolute value of the an. I'm not going to prove this, I'll leave this for you to do. Back to some examples. Is the series minus 1 to the power n plus 1 sine squared 1 over n absolutely convergent? Well, the first thing to note is if we take the absolute value of each term, we get sine squared 1 over n. So what we're asking is the series sine squared 1 over n convergent? I want to use the limit comparison test, and I want to compare sine squared 1 over n to 1 over n squared. So I do an divided by bn, then I take the limit and I get 1. That's a real number, and it's not equal to 0. So we can use the limit comparison test. The limit comparison test says either both of these series converge or they both diverge. We already know that the series 1 over n squares converges, so by the limit comparison test, the other one also converges. Therefore, the series absolute value of minus 1 to the power n minus 1 sine squared 1 over n converges, and therefore the series that we were asked for converges absolutely. I want to talk about version 2 of the ratio test, a more advanced version of the ratio test. Again, we're starting with a series. This time we're allowed to have positive numbers and negative numbers, but because we're going to be dividing by something, we can't have 0 here. We can't be dividing by 0. Suppose this time that the absolute value of an plus 1 over an converges to L. Now that's the only difference here. Just because we're allowed to have positive and negative numbers, we're just going to add in absolute values here. But other than that, the ideas are the same. If L is less than 1, the series is absolutely convergent. If L is greater than 1, the series is divergent. I'm going to skip the proof for today. You can read this in the slides later if you want. And this is in fact also true if we get the limit equal to infinity. If the limit is infinity, then again we get diverges. And what do we know if the limit is equal to 1? We know nothing. If the limit L is equal to 1, then the ratio test V2, just like the original ratio test, tells us nothing. Two examples from the textbook, or one example of two series from the textbook. First, 2n plus 5 over 3n. So what we do is we do absolute value of an plus 1 divided by an, take the limit, and we get 2/3. 2/3 is smaller than 1, so the series converges absolutely. Now, the book is making one more point here. This does not mean that 2/3 is the limit of the series. In fact, the limit of the series, or the value of the series, is 21 over 2. It's completely not connected to 2/3. This limit of the ratio only tells us if the series converges or diverges. And now let's look at the second one, 2n factorial over n factorial n factorial. So again, we do absolute value of an plus 1 over an. Take the limit and we get 4. 4 is greater than 1, so therefore this series must diverge. I have one final idea for today's lesson, the root test. Let's suppose that the nth root of the absolute value of a to the power n converges to some number L as n tends to infinity. Then the conclusion is the same. If L is less than 1, the series converges absolutely. If L is greater than 1, or L is infinity even, then the series diverges. I'm not going to prove this to you. The proof is in your textbook if you want to. And I just want to remark that just like the ratio test, if we have L equal to 1 in the root test, then we know nothing. We have to use a different test instead. Very quickly, 2 examples from the textbook. I'll pick out some key points, but then I'll leave the rest for you to read in your book. Let's suppose we're looking at a series where n is an odd number, we have an is n over 2 factorial. If n is an even number, we have 1 over 2 to the power n. Does this series converge? Well, we're going to try to use the root test. So we take the nth root. We either get the nth root of n over 2 or 1 over 2. So the nth root of the absolute value of n is always between these two numbers. Nth root of n. We saw this when we looked at n to the power 1 over n. This sequence we looked at last week, this tends to 1. So by the sandwich rule, the limit as n tends to infinity of the nth root of the absolute value of an is a half. A half is smaller than 1, so by the root test, this series converges absolutely. And final slide. 3 series, which of these converge and which diverge? 3 root series, root test questions. Anytime we have something to the power n, it might be a root test question. Anytime you see something to the power n in your series, have in the back of your mind, maybe we'll need to use the root test here. So each time it's the nth root of an and then take the limit. First one we get a half, that's smaller than 1, so it converges. The second one we get 2, bigger than 1, so it diverges. The third one we get the number 0. 0 is smaller than 1, so we get converges. And that is the end of this week's lesson. Next week we do not have a lesson. In 2 weeks' time we will have our final lesson. We will talk about alternating series and conditional convergence, power series and Taylor and Maclaurin series. Are there any questions?